Okay, good morning, everyone. I'm Saverio Romeo from Sapienza University of Rome, and I'm here to present you a new tool that is called Iris. It's a new photomonitoring tool for geohazard monitoring from space. Before starting, I would like to clarify the context in which we operate when we talk about photomonitoring. So, in the recent year, the technological development is allowing us more and more to use complex but low-cost instruments that acquire high-quality data. Very often, these data remain in a drawer and are not used for purposes such as surveying or monitoring. Please consider that in the last year, more than 1 trillion of pictures have been taken. The 90% of these from smartphone. So for this reason, we focus our work on the development of an innovative approach to process this large amount of data. A clear example of technological development is given by the world of drones. Here you can see that in the next few years, the commercial drone market will be increased, and this is true also for satellite platform. Our congress is about planet care from space, so this is true also for satellites. And at present, consider that we have more than 600 satellites for Earth observation, both with optical sensors, hyperspectral, and so on, SAR, and so on. Not only satellite and sensor, but also we have a large amount of data in our archives, more or less 20 years of data. So a lot to a large amount of data to be processed. In recent years, also new processing techniques and new applications have been developed in the field of medicine, agriculture, video surveillance, astronomy, and so on. So, in this framework, what is photomonitoring? Photomonitoring is a new, an innovative approach based on the comparison of different images of the same scenario, the same area of interest, acquired at different time intervals and sometimes from the same point of view. This photomonitoring allows us to perform difference analysis and movement analysis. What mean difference analysis? It's a change detection. Change detection, in other words, is the identification of changing features, new features, disappearing features as the red and black pixels below. Movement analysis is a displacement detection. So in other words, it's the identification and of course monitoring of feature translation, feature rotation, shift, as in the blue pixel below. So regarding the change detection, we can use a simple image difference. This process can be done by using a simple tool on GIS environment that is very, very fast, simple, but sometimes changes due to the brightness changes are not visible. For this reason, we can improve this process by using more sophisticated algorithms. For example, the structure similarity index, based on the indexing of results obtained from each pixel. About the displacement detection, the displacement detection is based on the movement of the detection of movement in horizontal and vertical axis. Based on the movement of the two axes, we can also reconstruct the oblique movement. So not only in horizontal and in vertical direction. And also, thanks to the displacement detection process, We can also detect movement below the 1 pixel range. That means that we are able to detect movement up to 0.01 pixels, so a lot. Sorry. So to summarize, photomonitoring can be considered as a monitoring approach, an innovative approach for monitoring with two main purposes: the knowledge to characterize and understand processes such as landslide or unstable buildings and glacier movements and so on, and control to monitor the evolution of this process over time. There are a lot of applications: landslide displacement monitoring, glacial displacement analysis. We can also create earthquake displacement map and so on. To ensure the reliability of the measurements, we can perform tests as we did in the laboratory by comparing data acquired by a reflex consumer camera and a total station by Leica, and by using a very small target with a random speckle pattern, we were able to detect some movement. Here there is the master image. This is the slave, so we cannot see any difference, but our tool sorry, was able to measure displacement of about 1.2 millimeter with a precision of 0.4 pixel. In this framework, taking advantage of all the experiences and issues gained in recent years in data processing, we developed, such as the use of not co-registered images, the brightness changes, the visibility, the rain, external object movement in our scenario. We developed this tool that is called IRIS, change detection and displacement analysis software. IRIS is software developed in Python environment, able to co-register, to make automatic analysis and so on. So here I show you some practical application performed by using images acquired by satellite. For instance, here we are in Arequipa landslides in Peru. We used optical satellite images from the PlanetScope satellite, and you can see here for each month we have one or more images, and our software was able to detect and to understand the amount of the displacement for each area. This is very important, and another important result was the drawing of the displacement vector on plane. So for each point, for each pixel, we can know the amount of displacement, but also the direction of this displacement. Not only, we also take some point within our study area, and we can extrapolate the time series of displacement or velocity. So this is a very important feature, in my opinion, because we can understand and interpret data, for instance, the increase of velocity, the acceleration of a given phenomenon. This is another important example. We are in southern Italy, Monte Scaglioso landslide, a very famous landslide. This is SAR images. So our software can process not only optical images, but also SAR images from synthetic aperture radar. This is the master, this is the slave. You can see some displacement, and this is the results with the displacement vector. Another example in Washington, USA, Rattlesnake Ridge landslide. We already realized the displacement map with vectors, and these are the time series of displacement for some polygon within the study area. And at last, this is the Rink Glacier. we used optical satellite images from Landsat. If I remember well, it's band 8 near infrared. This is the master. This is the slave. We are not able to detect any movement by our eyes in a qualitative way. But by using this software, this tool, this is the results. So we can see a core in a glacier with a movement of about more than 100 meters in less than 1 month, and displacement vector and so on. So this is our new tool that we developed both at university and at NAZCA startup company of the same university. And the software is available. So if you need some information, please write me at my email. Thank you.